You know, when we talk about building better AI, the conversation almost always goes to two things, right? More powerful GPUs and absolutely massive data sets. But what if that's not the whole story? What if the biggest hurdles are actually the ones hiding in plain sight?
Yeah, the common wisdom is basically, if we just throw more computing power at the problem, we're going to get smarter and smarter models. But is that really all there is to it? What if the real roadblocks, the things that are actually slowing us down, are things we're not even looking at?
So today we're going to explore two of these hidden bottlenecks. First, we're going to look at a really clever algorithmic puzzle. What happens when you have almost no data to work with? And then we'll dive into a massive infrastructure traffic jam that can bring even the most powerful hardware to a grinding halt. And for both, we're going to uncover some pretty brilliant solutions.
Okay, so our first challenge has nothing to do with hardware. It's all about a fundamental lack of data. This is a problem known as few-shot recognition.
So, what is few-shot recognition, or FSR? Well, imagine you need an AI to identify a really rare species of bird, but you only have, say, 16 pictures of it. And that's it. FSR is the challenge of training a model to become an expert with an incredibly small, almost insufficient amount of data.
And here's where it gets really, really tricky. The problem isn't just having a few examples to train with. The real nightmare is having zero examples to validate the model's performance on. How can you possibly be sure it's actually learning to identify the bird and not just memorizing those 16 specific photos you showed it?
This whole situation creates this huge divide. The in-distribution data, the stuff you train on, is tiny and perfect, but the out-of-distribution data, the stuff the model will see in the real world, is messy. It's sketches, weird angles, different lighting. The model has to somehow generalize from a perfect studio photo to a crayon drawing, all without a practice test to guide it.
So this brings us right to the central dilemma. As a model trains, it saves its progress. You can think of these as different versions or checkpoints. But how do you know which version is the best one? If you pick one too early, it hasn't learned enough. Pick one too late, and it's just memorized your photos. Without any way to test, you're completely flying blind.
This is where a research paper called VEST comes in with a genuinely clever solution. They found a way to create a validation signal out of what pretty much everyone else would just see as pure noise.
So here's the big idea. What if we just go out and grab a whole bunch of loosely related, kind of messy images from these huge open web datasets? We're not using them for training, no. We're using them as a kind of makeshift stand-in validation set. It's a bit like asking someone who's only ever seen professional photos of dogs to now identify a bunch of random dog doodles from the internet.
But here's the paradox. A model that's been specifically fine-tuned on our nice, clean photos actually gets worse at identifying the messy images. So if you just measure its accuracy on this noisy data, the best model is always the one you started with before you did any training at all. The validation method completely backfires.
To solve this, the researchers invented a brand new metric, and they called it the GF1 score. Now, instead of just looking at raw accuracy, it looks at the change in performance. It tries to find that checkpoint, that sweet spot, that gives you the biggest performance gain on the clean training data, while at the same time having the smallest performance loss on the noisy data. It finds the perfect balance between these two opposing signals. So the process is actually simple, but it's incredibly powerful. First, you grab that noisy open data. Second, you calculate the GF1 score at each and every training checkpoint. And third, you just pick the checkpoint with the highest score. It's just an elegant way to find the perfect balance between learning and memorizing, even when you don't have a real test.
Okay, let's totally shift gears now. We've seen how a clever algorithm can solve a data problem, but what happens when the problem isn't the data, but the hardware itself? Let's talk about the great GPU traffic jam.
So here's one of the biggest untold stories in AI infrastructure right now. GPU computing power has been growing exponentially, just off the charts. But the networks and storage systems that have to feed those GPUs, they're lagging way, way behind. And this has created a massive and still widening performance gap.
I love this analogy for the problem. Think of your high-end GPU as this hyper-efficient factory. It can process raw materials at incredible speeds, but it's completely dependent on a steady supply chain. And in this case, the network is the conveyor belt. If that conveyor belt is too slow, your multi-million-dollar factory just sits there, idle, waiting for data.
So where exactly do these delays happen? Well, it's mainly three places. First, just loading the data from storage to the GPU. Second,
and this is a big one for distributed training, is communicating updates between all the different machines over the network. And third, saving your progress by writing checkpoints back to storage. All of these moments force the GPU to just wait. So if the network is the bottleneck, what's the solution? Well, the answer lies in the network connection itself, and choosing the right one can unlock some truly unbelievable performance gains.
You've basically got two main options here. Most cloud setups default to standard Ethernet, which gives you about 1.25 gigabytes per second of bandwidth. But there's a specialized alternative called InfiniBand. It's designed for supercomputers, and it delivers a staggering 400 gigabytes per second. I mean, that's not a small difference. That is over 300 times more bandwidth.
So what does 300 times more bandwidth actually get you when it comes to training time? A 10-fold speed up. I'm going to say that again. Not 10% faster, 10 times faster.
The numbers here are just stunning. Training a massive 120 billion parameter model on Ethernet took almost an hour, 53 minutes. The exact same job on InfiniBand took just 7 minutes. The average time for a single training step dropped from almost 40 seconds to just over 4 seconds. That's literally the difference between going to get a coffee and coming back to find your entire training run is already finished.
And let's just zoom in on where that time is saved. A very common network task is called reduce scatter, which is basically just how all the different machines quickly share their updates with each other. On InfiniBand, it's a blink of an eye, 21 milliseconds. On Ethernet, it's over 10 times longer. And when you multiply that tiny delay by millions of steps, you see exactly how you end up with a 53-minute training run versus a 7-minute one.
So what's the big takeaway from all of this? When we connect these two stories, one about data, one about hardware, a really clear theme emerges. The path to better AI isn't just about going bigger, it's about being smarter.
The lessons are crystal clear. Algorithmic cleverness, like the GF1 score, can solve what look like impossible data problems. And smart infrastructure choices, like opting for InfiniBand, can unlock more speed than an entire new generation of GPUs might. It really shows that true progress often comes from tackling these hidden, unglamorous bottlenecks.
Which really just leaves us with a final thought. We've uncovered bottlenecks in data validation and network communication. It just makes you wonder, what other invisible walls are we about to hit, and what clever solutions are we going to invent to get around them?